but probably from the technique you learn something. It's really not a very important application in some sense, at least in operations management, which is kind of the main focus of our course in terms of application. And then there is a third problem. Unfortunately, I won't have time to cover it completely, which is the Adwords problem. So I'm going to show you a result, basically stating a result, a very classic result actually, but Adwords with machine learning predictions. In some sense, you have an algorithm that is allocating search queries to advertisers, and then imagine that there is a separate machine learning-based algorithm that is making recommendations, and you try to use that recommendation in decision making. So this paper is quite old, by Mahdi and Nazar Zadeh back in 2007. And I would say this is actually the paper that started this entire research line of learning augmented online algorithms. So there is this framework called Robustness-consistency framework. I'm going to talk about it when we are here, which is the kind of like now is a kind of a well-established framework in this domain. It started from this paper and then became way more popular back in 2008 by a paper by Nikolic and Vasilitsky. But I want to highlight that this is actually, I think, the first paper that started this framework. Did you know this paper, Mario? No. Right? They actually have a robustness consistency framework for Adwords there. I see. Giving the tight dependency on the trust parameter lambda for the problem. Okay, and remind me that, so there's an open problem. As I was preparing my lecture, I realized I don't know how to solve it. It seems to be very tractable though. It is related to the Adwords with ML advice. And I decided to pose that as kind of like a research topic for mini projects. This is a kind of like research topic that if you pick that one and you make a partial progress, you can consider it down so you get the full grade for your mini project, contingent upon writing the report and giving an acceptable talk. So remind me to tell you what that open problem is, and then we can even discuss that next week in my office if you were interested to work on. Okay, so let me start. So here's the first problem. So I'm going to look at the problem. I'm calling it the profit inequality. With single samples. Okay, so what is this problem? We know the profit inequality problem, but let me remind you for people that are attending the class for the first time. Imagine we have n buyers. Buyer I has a valuation for a good that you are selling, denoted by VI, which is realized from some distribution Fi. And then there is one item that we want to sell. The goal is, let's say, post a sequence of prices. Denoted by P1 to Pn. Such that expected welfare of your pricing is at least some alpha fraction of the expected optimum or maximum optimum welfare, which is defined to be the random variable, the max of the i's over all the i's. And here we are focusing again on welfare because we saw in the previous lecture that when you're trying to maximize revenue, you can reduce the problem to maximizing welfare by using virtual valuations. So if your goal is to maximize the revenue, as long as you have these results, you can map it back to the revenue question. So we are going to focus on welfare. And welfare of a sequential pricing, the ordering is known. So you post the first price P1, the first buyer comes. If the value is greater than the price, the sale is going to happen. Otherwise, you go to the next round, and the game continues until either the item is sold or you reach time. And usually we assume that these distributions are known. So here is how we diverge from the classic profit inequality assumption. Fi's are unknown. But you have access to one sample from each distribution, and that's it. Basically, you know, let me call that I tilde realized from distribution Fi, the single sample. Is a problem here? Yes.
Are we going to constrain FIs? Because if they're completely general, I guess there's no relation between VI tilde and VI that is going to be realized.
Not really. I mean, the only thing, in some sense, I'm going to use the fact that I'm not using any actually property. So it can be any sample from distribution. But so the sample is drawn from the original distribution.
Yeah, but if the original distribution is very general, so the next sample, which is the real VI, can be arbitrarily far from the.
It can be, but the probability of that event is kind of not that large. So
why? It is some kind of constraint on that.
I mean, at the end of the day, what I want to do is, I think what you are alluding is fun. So one can think about a type of guarantee that you want to say for any realization of these samples, you get a certain approximation. What I need is actually an approximation in expectation over the samples. So if you have an algorithm that uses these samples, at the end of the day, I want to say the expected welfare of the algorithm over all the randomness, including randomness in the samples, is at least half of the expected. That takes care of those kind of cases when the sample is not a very representative of the distribution.
So you're saying going from the expectation to high probability guarantee would be difficult without making further.
Yeah, because you know you might get like a sample that is just like an outlier in your distribution.
Yeah. Like you could have a mixture of like some distributions, and this is like from one mixture and from arbitrarily.
Too much to ask that for every realization you will be able to get a profit inequality result, but in expectation you can.
How is the welfare defined?
Just say expected value of the person that is the winner of the sequential. So the algorithm picks, let's say, some I. So you post this price to the first person that his value is above the price is going to be the winner. So the expected value of the winner is what they call the welfare of the algorithm, or the welfare of the sequence. So because we had this in the past, I didn't write down this version. So if you remember from what we know about profit inequality problem, there is actually a simple algorithm if you know the distributions that can give you a half profit inequality, basically alpha equal to half. That was that algorithm. There were several choices for a single threshold you could post. For example, you could post a single threshold equal to the expectation of max VI divided by 2, the op divided by 2. You could also look at the median of this distribution and post that single threshold, right? And we showed, if you know, basically know the distribution of the random variable max, therefore you can either compute the expectation or you look at the median, and either of those thresholds will give you a half approximation, and half is the best thing you can achieve in the profit inequality problem. So what we are going to show today is the following theorem. So theorem consider single threshold algorithm with t equal to any guess for what threshold I want to pick given the samples. So you want the threshold to be kind of a representative of the random variable max VI, and you have these n samples.
Yeah, we can create an unbiased estimator of that using
Unbiased estimator of
the V star. I don't know actually. Can we? The max of VIs.
I mean, if you look at the max of your samples,
Yeah, then that's not an unbiased estimator.
it is by definition an unbiased estimator.
For the distribution of the max.
Right.
Say one sample from that distribution.
Right. So one sample from the distribution is an unbiased estimator for
Right.
that distribution. For another sample from.
Yeah, I was
from the
thinking of
distribution.
just using.
But remember, like here, we were actually looking at op divided by 2, right? So if you know the underlying distributions, you look at the expectation of the max and then you divide by 2.
Yeah.
So one candidate is what Satish said, which is really like posting the max of the samples.
For median of the defined.
Median is also a good choice. I think looking at all these samples and then picking the median, I think is a good choice. Okay.
And that's guided from the fact that we know it works well in like a similar context. Is that kind of like the
You know,
motivation for it, for not
right.
picking the max?
So basically, if you look at the n random variables that you have and then you look at the median of those, then this is an unbiased estimator for the median,
Mhm.
right? Median of the actual realization. It's not exactly equal to the median of the actual realization. If it was, then that would have been a perfect choice.
Could actually be very fun. And I could have one distribution that's one always and others are uniform. Max is always one. But the median could be very, very bad. Median of the n sample.
Oh, so you're
could be
saying the
very
median
bad.
of the n samples is not actually unbiased estimator of the.
Not median of the max.
Right. That's not even an unbiased estimator. But I think instead you're right. So this is kind of killing the idea of median. So if you look at the median, so if there is just like, let's say one distribution. Right, so that one distribution is the one that matters. So you have to set your threshold for that one distribution. So median is not going to be representative of anything related to that distribution. So it's like deterministically one of the values is equal to 1,000, for example, and then you have a bunch of noise. So here the right threshold is really 1,000. But then when you look at the median of the samples, you're going to go with some number, which is pretty small. So it's not a good choice.
So we can say average the same way. Yeah.
I think we can think about all of these statistics, and I don't have actually a good intuition why, for example, we can't work with the max of these guys divided by a number. But let me tell you what the threshold that these guys is. It's actually the one that Satish mentioned. So basically, you look at really the max of your sample. So T is equal to the max of VIT, I in N. So you look at your samples, you set the threshold to be the max. You set that one threshold, and the first time a value goes above the threshold, that's going to be the winner. And then they show that expectation of value given by the alg is at least some fraction of the expectation of op. Do you have a guess what this number is? Do you think it should be smaller than half, or do you think half is achievable? Seems to be too good to be true that half is achievable, right? So you just have like one sample from each distribution.
Also, half there was like a direct consequence of the fact that the threshold had a term half, so that there was
Right,
a half
yeah.
probability of getting everywhere.
Exactly. So there was this
Here.
balanced notion. So you're using the balanced threshold, you could get half. And here it has nothing to do with the balancedness, right? So it's just like max of samples. But actually, it turns out that this is enough. We can get half of expectation of op, which is quite magical, I would say. And for those that haven't seen a proof of the property, okay, this can actually be a proof of the property quite problem. Then you know the distribution, so you don't need to really look at op divided by 2. You can just like take one sample from your distributions and now have a random example that will give you the required property required.
Does this mean our earlier analysis is true?
It's not. I mean, they lose in the sense that, I mean, what sense? So because half is tight. So our early analysis was saying that you can get half of the distribution knowing the distribution, saying that you can get the same half of the distribution without knowing the distribution, but it's only one sample. But half is the best thing actually. I'm not sure what you mean by.
But then, like, well, this is then certainly better because there we were required to compute in like integral over FIs. Here we only need a sampling oracle.
But
And still can
but
get
the
the
catch
syntax.
is this is a randomized algorithm, and it only can get this performance in expectation over its internal randomness, which are these samples. But then the other one was a deterministic algorithm. Knowing the distribution, it would just set this one threshold and take the half. So here, as we discussed, it's not the case that you can get the half approximation for every sample. Okay. So let's try to see why it works. And I would say the main reason that I want to show this result is because of this proof. So the proof of this theorem is using what is called the principle of deferred decision. I don't know if you have heard about that. So in some sense, this is a way to think about this, a different way to think about this problem. So one way to think about this problem is the following. So you have, n random variables v1 to vn, which are your actual values, and then there are n samples vi tilde all the way to vn tilde that are going to be given to you upfront. So basically, the samples are given upfront, and then you get to see the values one by one. Another way to think about this problem is the following. So I can generate 2n samples at the beginning. So imagine I generate 2n samples. How do I generate those? So from distribution I generate two samples, yi and let's say zi. Both are generated from fi. And without assumption, I assume that yi is greater than zi. I basically draw two samples from the same distribution. I call the larger one yi, the smaller one zi. Now, creates an instance of this problem in the following way. So rather than saying that, hey, these n samples are the samples, and then these other n samples are the values, I create my samples also in an online fashion. So at each time, I flip a coin. If coin flips one, then I say yi is my sample, zi is my actual value as it's realized. If coin flips heads, the other way. Right? So let's call these coins. So flip a coin, an unbiased coin. At each time I, from 1 to n. If coin is 1, then we say, well, so vi is going to be yi, and vi tilde, the sample is going to be zi. If the coin is 0, we swap that sign. So vi is going to be zi, and vi tilde is going to be yi.
You're assuming two sample access.
Two sample access.
No, one is the algorithm when you start running it, what you see in the.
No, but like generate 2n samples. That's two sample access.
Generate two samples in real time.
Yeah, I'm just saying that from the assumption, it seemed like we only had access to one vi tilde. But you're sampling.
No. Well, so 2n, not from the same distribution. So again, so your problem is the same problem. So you have only access to one sample from distribution. What I'm just saying is that you can assume that the algorithm doesn't get to see those samples all at the same time. Actually, so the algorithm is only having access to this, it's setting this threshold. And then when I'm analyzing the algorithm, I'm just saying this is the way that is 2n random variables, n from n that are samples and n that are the actual values of generated. I'm basically simulating my algorithm on this random instance, which is exactly the same as simulating it in the original random instance. Yes.
Maybe it's still a question, but if we are generating n samples and then n samples that are going to realize as our values independently from this n sample. So the internal randomness in our algorithm is independent of the sample patch that is going to be generated. So I don't know, it's kind of a mixing. So why not one of those thresholds is achieving the best output? I mean, the taus are random depending on what are our n samples. So why not one of the taus actually getting the maximum expectation?
So definitely one of the taus is going to be the best one, but
Why don't we get?
but you're saying like any randomized algorithm can be de-randomized. It can't be true. So you can't pick like I mean, so the thing is, you don't know which one of the taus is going to be the best one unless you know the entire value sequence we want to be in.
But aren't they independent?
Yeah.
And aren't we gonna consider for each one the expected overall sample realization sample time of VI?
So we have a randomized algorithm where the internal randomness of the algorithm is coming from essentially samples. And we say the expectation of the performance is at least, let's say, half of the opt. Then definitely there exists one of these random coins of the algorithm that was the best one.
I see.
But I don't know which one is the best unless I know the entries. Does it make sense?
Our final value in each sample pass is not, it depends on those VIs
Yeah.
and also our sample.
For sure.
So we cannot separate them. Okay.
All right, so again, what I'm trying to do here is just analyzing this algorithm by having an alternative view about this work, saying that, so rather than generating the samples up front and then revealing the values in an online fashion, I'm saying that at each time there is this nature that flips a coin. If the coin is 1, you call VI to be YI and VI tilde to be ZI. If the coin is 0, you do the other way. Okay, does it make sense? So, and then it is kind of clear that if you realize the random average VI and VI tilde in this way, then VIs are going to be independent from each other. VI tildes are going to be independent from each other. And VIs and VI tildes are going to be independent draws from the same distribution. Right? Just kind of like an easy way of realizing all the randomness that you need, but in an online fashion. Okay, now let's do the following. So suppose we have these two n samples, y1, y2, yn, and then we have z1, z2, z. Now here's what I'm going to do. I'm going to sort these numbers in a descending order. And after you sort these numbers, let's call the sorted list to be W1, now W1 is greater than W2, is greater than W3, all the way to Wn, and then Wn plus 1, all the way to W2. So note that when you look at each of these W's, you can say, well, so there was a time index associated to that W, or a distribution, index of the distribution associated to that W. And for example, for this W3, there is also a match somewhere here that these two guys are, one of them is the YI, one of them is the ZI. So one of them is, both of them are drawn from the same distribution. So what I'm trying to say is that I can define something like the index of Wj which is equal to I if Wj is equal to either Yi or Zi. Okay. Now, given this sorted list, you start looking at it and, well, so let's say W1 is from time, let's say 3. And then you have W2 from another time, let's say from time 2. And then you have W3 from time n. And then you have W4 from time 4. And then you have W5, which is, let's say again, is from time 2. And the rest of the sequence. So basically, you look at the sequence, there is a first time that you see the second sample from one of these distributions. I call that J star. And the way to think about it is, I sampled all these 2 random variables at the beginning, and I fix that. Given that, you can define J star. J star, we are going to call it the pivot. So pivot is defined to be the minimum J such that there exists an L smaller than J such that index of Wj is equal to index of W. That's exactly the mathematical definition of the first time that you see is. All right. Now here's the funny part. Lemma 1. I claim the expectation of opt, the max value, conditioned on these samples W's or Y and Z, it doesn't matter what you're exactly conditioning on. I'm not conditioning on the random coins. So I'm just conditioning on these realizations, but still my coin flips are random. So I'm just conditioning on those. If you take expectation of opt, the max condition W is exactly equal to summation J from 1 to J star minus 1 over 2 to the power J Wj plus 1 over 2 to the power J star minus 1 times Wj star. And let's try to show this. Okay, so what was our thought experiment? We had these random variables, y1 to yn and then z1 to zn. We don't know which one is sample, which one is actual. And when this happened, so we were going to call this thing the actual and this guy the sample, right? So this is the name that we picked for this two things. So in this case, so this is actual, this is sample. So now in this world, you want to look at the expected maximum value. How should you think about it? So I start flipping coins, right? So W1 is for some particular index. Flip the coin for that index. So if the coin flips in a way that Z is the, right, so Z is the, right, so if the coin flip is such that W1 becomes the actual, this is the largest number, so it becomes max. Does it make sense what I'm doing? So I'm looking at this list from the smallest number to largest, which is from the smallest index to the largest index, which is from the largest number to the smallest number. W1 corresponds to some index of W1. Look at the coin flip at that time. If the coin flips in a way that says, hey, this number, which is one of these Y's or Z's, should be the actual, not the sample, then because it's the largest number, this is going to be the maximum. Okay? when W2 is going to be the maximum, so if here the coin flip says that, well, so this is going to be sample, not the actual, but then 2 becomes the sample. So 2 becomes the actual, not the sample, then W2 is going to be the maximum, right? And you can, and by the way, so I'm using the fact that no 2 of these guys have the same index, therefore the coin flips corresponding to W1, W2, W3, all the way to Wj star minus 1 are all independent. So basically what I'm saying is that for J is smaller than J star, Wj is the maximum value if so if coin corresponding to index of Wj decides that Wj is an actual value. And for every j prime smaller than j, the coin corresponding to index Wj prime decides that Wj prime is a sample. Right? So if that's the case, then the first number that is an actual value will be Wj. So then because it's sorted, j is going to be the maximum value. Can any number after j star beat the maximum value?
I mean, it's decreasing.
So it's decreasing. And the funny fact is, once you pass j star, so you know that there was another number in the list that had the same index as j star. In this case, this guy and this guy are matched, right? So one of them is going to be an actual value, and it's going to be larger than all other Arabic numbers. No matter which one is that, so none of these guys can be a candidate for the optimum. So definitely opt cannot be any index after j star. So what about j star? Kind of the same logic, but with a subtle difference. When you think about j star, I claim that if all of these guys are samples, meaning that their coin flips say that these are samples, then 5 is going to be an actual, and that's it. Because the coin flip of this guy is exactly the coin flip of someone else here. So if you look at, for example, W5 here, W5 and W2, they have the same coin flip. So if the coin flip of this guy says that this is going to be a sample, definitely the coin flip of this guy says that this is going to be an action. So the only event that you need to look at is the event that everyone before J, if you look at their coin flips, the coin flip decides to put them as a sample. So for J equal to J star, Wj star is maximum value if for every j prime is smaller than j, coin corresponding to index of Wj prime decides that Wj prime is a sample. What I'm saying is that this event already implies that Wj star is an actual value. Because if by definition of J star, there is this L that has the same coin as J star. That L has already been in the sample set. Therefore, the other leg, which is J star, is going to be the actual. All right. So now, given these two, what will be the expectation of opt condition on W? So it's going to be some j from 1 to j star minus 1. So the max is going to be Wj if the two events happen, right? The coins corresponding to everyone up to j minus 1 should be saying that that W is a sample, and the coin corresponding to j should say that that number is actual. These are independent, each one happens in probability half. That gives you a half to the power j. For j star, you're going to have Wj star. The only event that you need to look at is that all the coins before j star minus 1, they should say that the corresponding W is in the sample set. The probability of that event is half to the power j star minus 1, and that gives it.
Sorry, could you repeat that? So the first one half is corresponding to like all the ones before J star being a sample. Is that the left-hand side or the right-hand side?
You mean this first term?
Yeah.
So this first term is looking at the event when one of the j's is smaller than j star becomes the maximum value. I'm saying if you focus on one of those j's, let's say wj, then it becomes the maximum value if everyone before that j has a coin flip that says that number is going to go to the sample list. And also when you look at the coin corresponding to wj, it says that that number should go to the actual.
Okay.
And there are j events, probability of all of them is equal to half, and they are independent, so the probability of the intersection would be half to the power j. And then you have to sum up over all the possibilities, j from 1 to j star minus 1. For j star, there is now one less event that you need to consider, because if the coin corresponding to this L is already saying that, hey, WL should be in the sample set, that already implies that WJ star should be in the actual set. These are two legs of the same thing. And the probability of that event is half to the power J star minus 1, because you only have J star minus 1 previous coins that you have to do.
So it also corresponds to the previous, the ones before it being samples.
Correct. And that's it. That's all you need for J star to be the winner. Okay. So that's lemma number 1. Lemma number 2. Is about the algorithm. What I want to say is that the expectation of the algorithm condition on vector W is at least summation j from 1 to j star minus 2 half to the power j plus 1 times wj plus half to the power j plus 1 times wj star, something like this. And if I made a mistake, we will see that in the proof. It will show itself in the proof. So how should we think about this one? So imagine again, I look at my sequence, W1, W2, W3, all the way to this WJ star. And we know that this guy has a match somewhere here, some WN. So look at the coin corresponding to index of W1. If the coin corresponding to index of W1 says that, hey, so let me write down one thing here. So this coin decides on who should be Y, who should be Z, right? And we always assume that yi is larger than zi. So if, for example, vi is equal to yi and vi tilde is equal to vi, then this is the case when the coin is equal to 1. And then
You wrote the opposite before.
did I?
Yeah, I have it written down.
Okay, I trust you. So, and then if vi tilde is vi and vi is zi, then this is the case when coin is equal to 1. So keep that in mind. So now if you look at, right, look at the event that says, hey, the coin index at W1 says that W1 is your sample. Then what would happen? So you look at the coin corresponding to index of W1, and this guy decides that W1 is a sample. We reject everything, right? Because your threshold was the max of the samples. And this guy is the max number among all the numbers that exist in this list of size 2n. So if the coin corresponding to W1 decides that W1 is a sample, then you're going to reject everything. Your sample is going to be the maximum number. Your threshold is going to be the maximum number. Okay, good. Now, look at this guy. So suppose the coin corresponding to index W1 decides that W1 is an actual value. And a coin corresponding to index of W2 decides that W2 is now a sample. What can you say about the algorithm?
I mean, then your reward is basically V of index of W2.
So this is a sample, so this never actually appears in your list.
Yeah, but
Well, so I'm looking at the event that W2 is a sample. So that means in the actual sequence of numbers that you see in the property inequality problem, you never actually see W2.
You get W1.
You get W1, right? So basically, if this guy is an actual value, it's not a sample, and this guy is a sample.
this is what you see. This is V index W2 tilde.
We index W2 tilde. What is W2 tilde?
V tilde of index W2.
Right.
So then you choose index of W2 because that's the biggest thing you see.
No, but this guy is not even appearing in your sequence of VIs.
Yeah,
I
I understood that. So its counterpart would appear in the actual sequence. You choose this index, you choose index of W2 based on your algorithm, right? Because this is the maximum across all the things you see.
Wait a second. So this is going to be my sample. This is going to be a sample, right?
Right.
That means my threshold is at least W2. That means no value in this list can be even accepted. Everything is everything here is going to be rejected. And then this guy, whenever it happens, is going to get accepted only if it is an actual value. If it is sample, you get nothing, which is the first case. Right? So let's try to formalize this argument. So this is basically saying that, let's say for J is smaller than J star minus 1, if the coin corresponding to index of W J prime decides that WJ prime is an actual value for every j prime that is strictly smaller than j. And the coin corresponding to index of wj decides that wj is now a sample. Then the best thing you can say is that whatever algorithm is picking is some number between W1 to Wj minus 1.
Could you clarify that? You said for all j less than j, is that like j star?
This is J prime. This is J prime.
All
So,
j prime.
so I'm looking at all the j's that are smaller than j star minus 1. I'm saying looking at this j, if the prefix up to that j, which is W1, W2 to Wj prime to Wj minus 1, if for all of those guys, their coins say that they are actual value. And then when you look at the Wj, its coin says that this is actually a sample, then your threshold is such that one of these numbers is going to be accepted. You don't know which one, but you can say your value for R is going to be at least the smallest thing at least, which is Wj minus 1. And I guess probably I'm going to make this Wj minus 1.
No, that's fine, I guess. I guess the problem is with the second term.
With the second term.
Yeah, it should be j star minus 1.
Ah, maybe you're right.
And the
And you think
power should be j star minus 1, I guess.
we are going to figure
Yeah,
out the right thing after. But
Because
You do accept W1 whether
Yeah,
it's
you'd accept
1/4
W1, right? Why Wj minus
With
1?
1/4 probably you'll accept it. So it's fine.
No, wait. Here I'm confused. Why are you saying greater than equals to Wj minus 1? It should
I
just be
mean-
W1.
Wj.
no. So
So
we don't know the ordering of W1 to Wj minus 1. They can come in any order. So the earliest of those guys is going to be accepted. We don't know which one is
Oh,
that.
right. So yeah.
And that will be Wj minus 1. And you mentioned you are going to
You can
give
accept W1, right? If the second event happens. So with 1/4 probability you could accept it.
here, right? So here, so in this case, if you're just looking at it, you're definitely accepting W1.
So that way Wj brings us because with 1/4 you get W1, so that's okay.
you shouldn't have changed it. It was okay. But it should be Wj. That was fine.
Oh, because okay, I see. Okay. Now I see what's just. It's like the same thing, but okay.
Because you're going to J star minus 2.
Basically, I need half to the power some j times Wj minus a. So this index should be one number larger than this index. That's all. Right. And the first term you're W1 times 1. Okay, so let's continue. Now, what else you can say? So thinking about Wj star. It's kind of like similar to lemma 1.
So here you need j to be strictly smaller than j star minus 1
Right.
because
I'm actually looking at now j equal to j star minus 1. Not j equal to j. So look at j equal to j star minus 1. I claim that if for every j prime, which is between 1 and j star minus 1, for every j prime that is between 1 and j star, the coin corresponding to index of For every j prime is between 1 and j star minus 1, if the coin corresponding to index of wj prime decides that wj prime is an actual value,
-1.
yeah, I don't know why it should not be, but if a coin corresponds to index of wj prime, it says that wj prime is an actual value. Then, first of all, this already implies that the coin corresponding to wj star is going to say that wj star is going to be a sample because of the fact that L has already appeared in the sequence. So this already implies that the coin corresponding to index of wj star besides the wj star is a sample. And this implies that your threshold is going to be exactly wj star. And therefore, the algorithm is getting one of the values from 1 to j star minus 1 to show that this is at least wj star minus 1. Does it make sense? So the only difference is that I don't need to look at the end of these two events because the first one already implies the second one. And again, your coins are independent. So now let's write down the expectation of and the condition on W. So this is at least summation j from 1 to j star minus 2. And then we have half to the power j. So j from 1 to j star minus 2, and then I have half to the power j plus 1 times wj.
What's the plus one? You just have j conflicts.
Yeah, so I imagine, so this is basically j from, right, so w0 is 0, right?
0.
And then you start from w1, and then the multiplier of w1 is basically 1/4, right? So if this coin flip says that this guy is an actual and this guy is a sample, then you get w1, so it's 1/4. Yes.
Why you didn't consider j prime strictly n less than j star minus 1, that those are actual and j star minus 1 is sample? You haven't considered this case.
j star minus 1 is a sample? Because
Because that would be better now.
Yeah, but we haven't written that.
It is one of these cases.
Yes, it is the last case of.
last case of this is that, right? So if
No, that one was j.
I mean, here you're basically looking at wj minus 1. So the last case here is w. Anyway, so this should be, yeah. Wait, what I'm doing here. So j at most j star minus 1. All I want to do is that the j is at most j star. I think what I want to do is the j is at most j star minus 1, and this is j equal to j star. And then for every j prime is smaller than j star minus 1, this is what I want. Right.
That That would change
Because this part is really talking about fixing some j, you talk about wj minus 1 and whether you get that or not. When j is equal to j star, you're talking about wj star minus 1. Is it now consistent? Let's read everything from the beginning. So for any j from 1 to j star minus 1, I want to show under what condition you get wj minus 1. That covers all the w's from 1 all the way to j star minus 2, which is the first summation. And then for j equal to j star, I want to see what is the condition I get wj star minus 1. Right? And the condition is that all the j primes from 1 to j star minus 1 should say that their coins should say that they should be an actual value. And that automatically implies that j star is going to be sample. So your threshold is going to be equal to wj star. Therefore, you're going to win a number between w1 all the way to wj star minus 1. This is the only lower one. And the probability of that event is half to the power j star minus 1, and then you get wj star minus. Okay. Yes.
So the first term is basically probability to get one of the ones that are before j star minus 1, and the 1/2 corresponds to them being actual versus sample, right?
Correct.
Okay, and then
Right. I guess I can write this in a nicer form. Maybe that's a little bit helpful. So this thing is half times half to the power, let's say j star times j star minus 1 minus half to the power j star minus 1 times wj star minus 1.
can you repeat why the first index is j plus 1? And in the the power of 1/2, yeah.
Here? Okay, so the first term is W1, right? And this is corresponding to j equal to 1 here. So it corresponds to j equal to 2 here. So basically for j equal to 1, you get nothing. So j equal to 1, because you're looking really thinking, you look at basically W0, which is 0. So for j equal to 1, you get that. For j equal to 2, you start getting something. So you get W1 for j equal to 2, only if the W1 is an actual and W3 is a sample, which happens to approach 1/4. So the first term should be W1 times 1/4, and this is exactly what you get at j equal to 1. Yes.
For that one, you wanted to we can underestimate that with 1/2 j star.
Let's do it in the actual theory. So the final proof is just one line. So expectation of opt condition on W, what that term is summation j from 1 to j star minus 1 half to the power j times wj plus half to the power j star minus 1 times wj star. And that's the expectation of Av. So I claim, let's write it down. So expectation of Av condition on W is equal to that term. So I claim this is greater or equal than, first of all, this is equal to half to the power j star times w j star minus 1 plus half to the power j star times w j star minus 1, right? And then merge this term with this summation. It's going to be greater or equal than j from 1. The last term now is going to be j star minus 1 half to the power j plus 1 times wj. This is by merging this term into this summation. What about this term? The wj star minus 1 is greater or equal than wj star. So I'm just replacing this one with wj star. That gives us something like 1/2 to the power j star times wj star. And now compare these two. This is greater or equal than, this is actually equal to half times expectation of opt condition. And that's it. So back to your question. So actually, this is kind of like a point-wise argument to some extent, meaning that I don't care whether the two n numbers that I'm drawing at the beginning in this new interpretation, this deferred decision interpretation, are even bad. So they can be any arrangement. But then I need to take expectation or the randomness in my coin. In that sense, it is semi-pointwise. But really, what you are going to get at the end is that the expected performance of the algorithm over all the randomness is at least half of the expected output. All right. That should be proof. Any questions about this one? Yeah.
So the classic profit equality was like we get infinite many samples, right? And
In
we
some sense,
prove-
right. So basically, if I give you infinite many samples from each distribution, this is more or less similar to giving you the distribution. And then you can get half of it.
So we prove only one is enough.
Yeah.
So for the earlier one, the objective is maximizing revenue.
So we discussed the original profit inequality problem where the objective is maximizing welfare. And then there is a sequential posted pricing with the objective of revenue. So we showed last time that the sequential posted pricing with the objective of revenue can be reduced to the profit inequality problem. Basically, by using the virtual valuations, you can reduce the revenue objective to welfare objective. And then for the welfare objective, the profit inequality result says that, hey, there's this threshold so that the expected value of the first buyer that exceeds the threshold is going to be at least half of the optimum. And
That
also
we-
there is a max.
That you can't do with this because of virtual value, you need the
Exactly.
distribution, so this can't be combined with that.
Exactly. So if for example, I give you a sample from the virtual values, then you can do the single sample profit inequality for the objective of revenue. But with single sample from the actual distribution, you can't do that trick. So the trick that we used last time, if you remember, was, hey, so I'm running a profit inequality algorithm on the space of virtual valuations. So you pick the threshold T to be the expectation of the revenue of the optimal Morris function divided by 2 in the space of virtual valuations. And then that threshold will be translated into the price in the space of values by applying the inverse of the virtual value function. So this step cannot be done here because you don't know the distribution, therefore you don't know the virtual value. So if I tell you the virtual values and give you a sample, that can be done. If I give you a sample in the virtual value space, now that I think about it more, I don't think it can be done.
Unless you also see the virtual value.
Right, unless you see the virtual value. So basically, the bottom line is for the objective of the revenue, this breaks. And it will be interesting to see what can be done with the revenue. Having said that, I should say one very interesting result. Suppose I'm selling an item to you, and your valuation is regular, meaning that your virtual value is monotone. Suppose I don't know your distribution, but I have one sample from your distribution. Then if I post that one price, then the expected revenue I extract from is half of the expected revenue I could extract from optimal marks. It comes from this geometric interpretation. Last time, if you remember, we were talking about revenue curve in the quantile space, which was this function starting from 0 going to 1. And there is this optimal quantile for sale, which gives you the optimal marathon corresponding to the monopoly price in a single item, single buyer case. If I give you a sample from the distribution, that corresponds to picking a quantile uniform 0, 1 random value, and then posting that quantile. right? Because if you look at the sample from your distribution, the quantile corresponding to the sample is a uniform 0-1 random variable. And then how much you can get from a randomized quantile, which is a uniform 0-1 random variable. So basically your revenue would be the area under the revenue. Because for each quantile Q, you get this amount, and it is uniform 0-1, so take the expectation, so the revenue will be the area under the revenue. But then the optimal milestone revenue is the peak times 1. So this is 1, this is 0. This 0 is 1. So the optimal milestone revenue is actually area under this rectangle. And if your distribution is such that revenue curve is concave in the quantile space, meaning that the visual is monotone, then the area under the revenue curve is at least half of the rectangular's area, because this triangle gives you exactly half. This is more than a triangle, so that gives you more than half.
That's just like Boolean comparative proof also that like one rand.
Right, so this is kind of like Boolean result for 2 buyers. This is a proof for that. But then for n buyers, you need to be a little bit more careful.
This is interesting because if you don't have regular distributions and you are doing ironing before choosing some, then would your expected rewards still be the area under the ironed revenue curve?
Correct, but the thing is with one sample, you don't know whether that sample lands in the ironed interval or not.
You don't have, yeah.
If you knew the sample is landing in an iron interval, then you could get the half of the revenue from the iron virtual curve. But because you don't know that, it's not possible. These are all interesting questions, I think, that one can answer. So how about having a short break, maybe, let's say for 7 minutes, and then we'll be back.
What is seconds? Okay, how many seconds? Interesting, but like it's not even clear. Like if you have 3 samples, how do you improve the algorithm in what manner? Like I guess the variance reduces for the welfare, but like how? It's not clear here actually. But it's nice.
Yes, this has been a study the asymptotic when you have a lot of samples. And we know the right dependency on the complexity ratio to the number of samples in the asymptotic. But I don't think the entire spectrum has been identified.
Shouldn't it be possible to, like for finite samples? So initially when you gave that assumption, I thought you were going to use that thing as an unbiased estimator for the mean. But the proof itself is like not exactly that way.
Right.
It's so yeah, so like yeah, it is symmetrization. So like I don't know how you will use like finite samples and still get this kind of a proof. Because you said the variance in your estimate is reduced, but how do I use that?
Yeah, so basically the asymptotic regime proof is using
So the asymptotic
concentration bound in some sense. And that's these kind of statistics are getting more and more centered around what you need for getting the half approximation or the right probability.
Right.
But then, yeah, the middle ground region, I actually don't know how to extend this analysis. I think it's a great question.
I guess you need to go beyond this metric because this metric will only tell you the expected reward. But how do you prove concentration of competitive ratio in some sense? That also, I guess, it's
also, I don't know the answer to your question. Maybe given one sample from each distribution, you can somehow still get a half approximation or constant approximation. I think actually you can get a constant approximation, but I'm not sure if you can get a half approximation. You can get a constant approximation by somehow dividing.
I'm not even sure, right? Because you can have distributions with infinite expectation, but with high probability, I'm small. So my sample could be small with very high probability, and I could set that as a threshold, and I'll just get some very small.
Also, so definitely the threshold shouldn't be the max of the samples we see. But you might be able to do something else. I'm trying to recall. So there is this prior independent mechanism design literature. When yeah, I don't know the answer off the top of my head, but how to get an air constant.
Also, such distributions don't exist on compact supports, right?
Yeah, so that if you bounded support, then I guess yeah.
By the way, now that you mentioned, I wish I had covered Euler-Kelemper too. Given this, I think it would be a very nice
If
natural
geometric
complement.
proofs was too. Is it also like can you state this?
For the, I mean, Euler-Kelemper is one line proof, right? So let's say we have n buyer, n plus one buyers, right? Then I can say among all the options that are forced to sell the item, second price auction is the one that maximizes. Right? Now, here is one other auction that always sells the item. For the first n buyer, run optimal marathon. If optimal marathon decides to not sell, give it to the last buyer for free.
Yeah.
So therefore, this is another auction in the class of auctions that always sell the item in the n plus one buyer setting. Its revenue should be less than the revenue of the second price auction. Therefore, we look at it. In some sense, I could do the same thing here as well, right? Saying that the revenue I get here when I post a sample is the revenue you get from the second price auction with two buyers.
But with half probability, I'm the one who's the
Correct.
fake buyer. Correct.
We did. First, I don't know about what you're talking about, but the auction you mentioned, how is that revenue equal to second price revenue?
No, so the Euler-Kelemper is also saying that in IID setting, if I give you one more buyer and then run VCG, second price auction, then the revenue you will get is going to be upper bounded on the revenue of the Meyerson on the original in the original auction, in the original pull-up buyer. So n buyers optimal Meyerson is weakly dominated in terms of expected revenue by n plus one buyer second price auction.
Okay.
That's basically
intuitive because VCG's revenue should be
Not
less than
intuitive
equals to
actually.
second price's
it's
revenue.
not intuitive. I don't.
No, second price. So the revenue of second price auction and VCG should be the same.
This is welfare. It doesn't say anything.
No. It's a welfare. Yeah. Okay.
I mean,
The one virtual line.
it becomes a little bit more intuitive because in a symmetric setting, at the end of the day, you really want to pick the highest value buyer only if the highest value buyer passes the reserve price. And somehow this last buyer, by adding a little bit of more complexity, is playing the role of that reserve price. But the formal argument is what I told Varun, that hey, I have n plus one buyers, I run the second price auction. So second price auction among all the auctions that are forced to sell the item.
Yeah.
Is the one that maximizes your revenue.
Okay.
So now here's another auction that always sells the item. Run optimal marathon
Yeah.
for the first n buyers, and then if the optimal marathon decides to not sell the item, give it to the last buyer.
Yeah, but how is the revenue?
Oh, so this is feasible in the class of auctions that sell the item.
That I agree.
So therefore, and revenue of the second auction is revenue of optimal marathon for n buyers.
Yes.
So therefore, the revenue of the second price auction for n plus one buyers is greater for the revenue of the marathon for n buyers. And that's the Euler-Kelemper.
So the second price for the first 10 buyers is equals to the optimal Meyerson for the first 10.
Second price for the
If it chooses
first
to sell.
11,
Okay.
let's say I have 11 buyers, right? So the second price auction for all the 11 buyers will give you a revenue that is upper bounded by Meyerson for the first 10 buyers. So Meyerson for the first 10 buyers is not second price. Second price with some reserve price.
Yeah.
Sometimes it doesn't sell the item if none of the buyers can pass the reserve.
Why is it upper bounded?
Because the auction I mentioned, the one that runs optimal marathon for the first n buyers. If that auction decides to not sell, give it to n plus one for free, always give the item to someone.
Right.
And this auction is just one of the many feasible auctions in the class of auctions that always sell there.
Yeah.
And among those, second price is the one that has maximum revenue.
Right? Second price for the 11
For the
buyers.
So now nothing of those 11. So in that problem, the expected revenue of second price auction is going to be greater than the expected revenue of the other alternative auction,
You mentioned, yeah.
which is the milestone for 10.
Myson for 10, otherwise give to 11.
Yeah, but you give to the other guy for free. So the expected revenue you get from this auction is exactly equal to the expected revenue for 10 buyers. So you only make revenue if sale happens within the first 10. Otherwise, you don't make any money.
The beauty is that mechanism is useless. Just get one more buyer.
Yeah.
And just do VCG. Like don't worry about designing
But
mechanisms.
it only comes because of the symmetry of them. Right?
Yeah, that's
So
fair.
everything
Right.
breaks when you. Having said that, if you have n buyers and then you have one copy of each buyer, then again second price auction is giving you a council approximation for optimers. I think it's a 4 approximation.
I can take that actually. Yes, how much is it charged?
16.
Oh, that's good. Good enough.
So consistency. Robustness, right?
She also like a lot of learning films.
The other day, I was talking to Nathan about some optimization problem and online convex optimization problem. And someone asked, okay, what's the application of this problem? And I said, inventory management is an application. And everyone recognized I'm attending this class.
Okay. That's good. You know, we are corrupting CS folks with folks.
It's a battery charging you like that.
Is that it? Yes.
Okay. Okay. So in the second half of the lecture, we are gonna think about online algorithms when the algorithm is endowed with some sort of machine learning advice. And this is not completely well defined. What does machine learning advice mean? How do you define predictions, etc.? I think part of the reason that there is a lot of interest in this area is because these questions haven't completely been solved yet. In different contexts, how should you view the predictions? How should you view the advice, etc.? But then the philosophy behind all of this is kind of the same. So what is the goal? So imagine you are designing an online algorithm in an adversarial environment when there is no assumption on the input instance as it arrives. So this seems to be a very pessimistic view about the world because we're trying to design a quote unquote robust algorithm that no matter what input is arriving, generated by the adversary, you perform well. But then maybe you know something about the input instance. Maybe you, for example, even know part of the input, maybe there is an algorithm that can predict the input. Maybe that prediction is not good, but still you have access to that. And now the goal is to design basically an online algorithm that if the prediction that you have access to is a good prediction, you will be close to the optimum. Like for example, suppose you have access to a crystal ball that can really predict the future and give you the optimal solution. If that is the case, you would like to be pretty close to optimal. And then if it is not the case and your prediction is having a lot of error, so you try to be as good as the original solution that didn't meet the prediction and wanted to be competitive against all the problems. Right? So this is kind of like a game between a robustness criteria that you want to still be competitive no matter what input instance is realized, and a consistency criteria, meaning that you would like to be close to your prediction so that if it happens that the prediction is a good one, you end up with getting much better solutions versus the original ones that you could get by having the pessimistic view. But then the question is, well, so I should kind of like define how much I rely on my prediction, how much I trust my prediction. And this framework comes with a parameter. We are going to call it the trust parameter. So lambda, the trust parameter. The way to think about this is that if lambda is equal to 0, for example, we trust the prediction fully. And therefore, we just follow the solution that is advised by the prediction. And then the other side of the spectrum is when lambda is equal to 1. So in that case, we don't trust the prediction at all. And usually when you design an algorithm in this domain, when lambda is equal to 1, you really want the performance of the algorithm to be close to one of the competitive algorithms in the adversarial version of the problem. So in this case, we try to be competitive against forces. And somehow the goal is, given a parameter lambda, which indicates how much you trust your prediction, get the right trade-off between what they call robustness and consistency. What does mathematically this mean? So let me define some notations. Think about the cost minimization problem. So consider the cost minimization problem. Okay. And suppose an algorithm is given, suppose an algorithm is given, then phi of alg and let's say I and lambda, I'm going to define it as the cost of algorithm with trust lambda on prediction over the input instance over input instance I. So for example, if you look at the cost of I and lambda equal to 1, this is basically what the algorithm gets, it ignores the prediction. And then if you look at the cost of alk in I and 0, this is basically what you get if you follow the prediction. Okay. Let me.
Excuse me. So lambda is not just our trust, it's the correctness of the parameter.
No. So
It's just our belief.
it's just our trust. So basically, we might trust the prediction, but the prediction is not good. In that case, you don't expect much. So if I formulate the robustness and consistency, you will see what do I really mean. So what do I want? Let me define the, let's say, E of I. Actually, let's say cost of P of I and lambda. This is basically the cost of following the prediction, whatever that means. And this is kind of context dependent, so I'm gonna leave it open. What does that exactly mean? So cost of following the prediction. And one other last thing, so C of, let's say, opt of I and lambda is basically the cost of optimal solution. Basically means that, well, so given an index, given instance I look at the best offline solution. For example, in an online algorithm problem, in an offline problem, really the best solution.
Because this does not depend on lambda.
Correct. But for the sake of like notation, it's just a kept it here, but it doesn't really depend on that. Okay, so now we say an algorithm is, let's say, C lambda consistent and R lambda robust. It's the following holds. We want for every instance I, and I'm thinking about maybe randomized algorithms, we take the expectation. Or let's include it in the cost. So when I say cost of I and lambda, if I was a randomized algorithm, imagine we get the expected cost. So this is going to be the expected cost. And then I'm not following this in expectation. So for the deterministic algorithm, this is really the cost. For randomized algorithm, this is the expected cost, where the expectation is over the internal randomness of the algorithm. So for any instance I, what I want is that I'm not that far from following the prediction. Basically, the cost of alk, I and lambda, let's say is at most C of lambda times the cost of following the prediction. But then at the same time, you kind of want to be competitive. So for every instance I, you want the cost of the algorithm to be at most R lambda times the cost of the optimal solution.
So the prediction is always deterministic?
I can't think of an example in the literature where the prediction was random.
Could you elaborate on what do you mean by cost of following the prediction versus
so-
having the algorithm be like lambda equals 0?
Right.
Because
It's kind of the same thing, right? I mean, it's the cost of the optimum algorithm when lambda is equal to 0. Not necessarily my algorithm. So maybe my algorithm never actually follows prediction. A meaningful algorithm would be something that if lambda is equal to 0, which means that you have 100% trust on the prediction, you follow the prediction, but I don't want to restrict the algorithm to always do that. This is why I define the PI instead. So think of PI as an algorithm that trusts the prediction and does the optimal, basically
I see.
does the optimal thing given the prediction, something like that.
I did, because I guess you're avoiding the instance where you think the prediction is super, you can trust it a lot, but you don't listen to it, you leave there anyways.
But I think your intuition is absolutely correct that when you design an algorithm in this domain, if lambda is equal to 0, so your algorithm should do what PI does, but I'm not restricting to that class. You might do something crazy. Yes.
The C lambda and R lambda, they're functions.
They are functions of lambda and they should have some property. So even though, so you can say an alg, so this is basically a definition. So you say definition, an alg is C lambda consistent or lambda robust, and you can always find two functions. You're gonna be happy. So your goal is basically the following. This is pretty important. So if I put no trust, okay. So if we right, so if lambda is equal to 0, which means that I'm trying to follow my prediction, then we want the C0 to be kind of equal to 1. And then when lambda is equal to 1, which means that I don't have any trust in the prediction. So what I want is the R lambda to R1 to be a constant as close as possible to the optimal, let's say, competitive ratio or approximation factor in an adversarial set.
Why it should be as close as possible, but shouldn't be exactly.
Sometimes we can't get the best of both worlds. I mean, that's the ideal case. That your design is such that when lambda is equal to 1, I mean, you can always say, hey, if lambda is equal to 1, I forget about everything, but usually when you design these things, you try to also be smooth towards your parameter lambda. So you don't want to do something completely different with lambda just is equal to 1. Otherwise, you could satisfy this constraint. But I guess, so what I'm trying to say is that for every lambda, you try to keep these numbers to be acceptable constants, but at the same time, you want C0 to be around 1, R1 to be a constant, ideally the optimum competitive ratio of the adversarial problem. What about C1, for example? I think this is important.
It should be less than.
So when you don't trust the prediction at all, lambda is equal to 1, you still want your C lambda to be a constant, or C1 to be a constant, but you don't need C1 to be a large number anymore. So basically, you only need the, right, so basically, if you trust the prediction, and the prediction is a good one, you want to be close to optimal. But then, if C1 is very small, that means that you don't trust the prediction, even though if your prediction is very accurate, you might not perform well. So you try to have as large C1 as possible. But I mean, in some cases in this literature, I have seen the case that C1 wasn't actually constant. But ideally, you want to keep C lambda and R lambda, no matter where lambda is to be constant. Just want to highlight that the meaning of C lambda when lambda is equal to 1 is that, hey, I'm in a situation that I don't trust my prediction, but maybe your prediction is pretty accurate. So in that case, you're still going to get a constant, such that if that constant is more than what you can get in the adversarial problem, you beat the adversarial algorithm. But yeah, I think that's the extent which I can tell you about this trade. Is the trade-off clear? Like so you have the trust parameter. Yes.
I'm sorry, we want C1 as large as possible.
Correct.
But the one that the reason you mentioned, it was better to have C1 as small as possible.
No. So I want C1 to be. So it's a cost minimization problem. Or did I say?
It should be as small as possible.
Oh, okay. So this is a cost minimization problem. So we want this factor to be as small as possible. So basically, what I want is that C1 to still be a constant. Ideally, I definitely want C0 to be 1. And then C1 is going to be the largest constant I get, but I want it to be as small as possible. There is really no restriction on that. You might be in a case that C1 is not even a constant. That is allowed in some sense, but this is not the ideal situation. Let me rephrase some of the stuff I'm saying. This is kind of like an engineering approach towards online algorithm design. And there is an extent to which how much you can keep these numbers small. And depending on the application, you might play around with these things and first change your trust parameter, and second, even change your design. Ideally, you want these numbers to be all small, but this is not possible. There are some information theoretic bounds on how small the consistency parameter can be for a given, let's say, upper bound on the robustness and vice versa. You try to be close to that Pareto frontier.
I don't understand what you mean C1 might not be a constant. If it's not a constant, what is it a function of?
Basically, imagine, for example, in some problem instance, C lambda is always a constant if lambda is smaller than, let's say, half. If lambda is greater than half, it becomes log, something like that. Then this is a scenario that C lambda is not a constant. Still, it is allowed in this literature, but not ideal.
What is n?
Size of the problem.
Okay, so you ideally want C1 to be small because it's a cost minimization problem, but you are fine if it's some reasonable dependence in the size of the instance.
In some sense, but basically your goal is
The
to
second one will bind, right? The R lambda will bind, so that's fine. Doesn't matter what C1. Even if it's log n, R lambda C opt will
Yeah, it's
bind.
just an upper bound, so.
no. So as long as R lambda should definitely always be a constant. So you don't want to be very far. So that means if C lambda, let's say C1 is log n, it doesn't mean that your performance is bad. Your performance now is going to be bounded by the performance in the adversarial system. But if C, let's say even 1, is a good constant, imagine it is smaller than even R lambda for all the lambda. Then if it happens that the prediction is accurate, even if your trust is small, then you're going to get a good performance. So there are two things that you have to consider: whether you trust the prediction or not, how much trust you have on the prediction, and the second way is how much prediction is accurate. Your ideal scenario is that when you trust the predictor and the predictor is accurate, you get near optimal solution. But all other possibilities are optional. If they are achieved, that would be great, but not necessarily a requirement when you design an ML algorithm.
Ideally, you want the minimum for any lambda, and for any lambda, you want the minimum of C lambda and R lambda to be small. So that either of these upper bounds you can basically use to upper bound your cost.
Right, because you don't know how accurate your predictor is. But if, for example, in an application, I tell you, hey, your predictor is pretty accurate, then you put more weight on C lambda. And that's a scenario that you even don't want the C1 to be very small, very large in the cost minimization problem. So if I tell you that, hey, Satish, so you have this predictor, and it is actually very accurate, now design an algorithm, then your tendency is to design an algorithm where the C lambda is as small as possible. And even you try to minimize the C bar. But if you're in a domain that you don't really know that much about the predictor, then you can say, well, so I try to set my lambda based on how much trust I have on the predictor. And then for that lambda, I want C lambda to be massive.
I guess I'm confused about a couple of things. One is like, how is ALG a function of PI and lambda? Because it's certainly a function of PI, lambda, and maybe some other computation is happening, right? The algorithm. It is some function of what the predictor predicts on the instance, how much I trust the predictor, and what my fallback option is.
It's just a cost, right? So
No,
the prediction,
not the
follow
cost,
prediction.
but the algorithm's actual output on the instance. I guess we've not specified yet how is it a function of PI and lambda.
Not yet. I mean, that's the definition of the algorithm. So you have access to this prediction. You also have this parameter lambda. You kind of use lambda and PI, and that returns the final solution.
Right. So I'm just saying, why not simply?
I think many of these confusions are going to be solved after I give you an example, because this is a very abstract model.
Yeah.
Many things, even in papers written in this literature, are not well defined. Just, hey, so we keep it open. We want to be competitive versus the predictor. We want to be competitive against any algorithm, and we try to make these things as small as possible. Let's really find the right trade-off between C lambda and R lambda. Yes.
I'm confused. We design an algorithm, then we can provide C lambda and R lambda for that algorithm. Yes.
But your algorithm is using lambda.
Yes.
as a parameter.
Yeah. But what do you mean minimizing C lambda and R lambda?
Like for example, let's say I can show you a lemma that there is a certain problem instance that on that problem instance, if you want to be better than C lambda competitive against your predictor, you definitely can't be R lambda competitive on that instance. Then this gives you a trade-off between C lambda and R lambda.
Yeah, but our algorithm still has its own R lambda and C lambda. What you provide is only an upper bound,
This
for
should
example.
hold for every instance. So you give me an algorithm that uses your predictor and lambda in some way. And then I can basically find out the worst case competitive ratio against the predictor and the worst case competitive ratio against the optimum of 9.
Yeah,
These are defining C lambda and R lambda.
yeah, that would be, for example, C algorithm lambda and R algorithm lambda. What you said previously, and that provide a relation between C lambda and R lambda.
For a specific algorithm.
No,
And try to design the algorithm in a way that the curve C and R that you get for different lambdas is as small as possible. As a 2D parametric curve. So imagine some algorithms, I'm looking at C and R, okay? Let's say for some certain algorithm, as you change lambda, RC curve is going to be something like that. And then there is another algorithm where the RC curve is like that. Which one is better? Then I say this algorithm is better.
okay, but what?
So you want to find these parameters.
Yeah, what is the minimizing algorithm? What does it
The
definition?
minimizing algorithm.
You wanna find the algorithm that minimizes over those curves, yeah?
So let's say I give you some certain lower bounds. What does that mean? So for example, I say, hey, given a parameter lambda,
There exists no algorithm that can get better than that.
yeah, so you can have basically achievability regions, right? So there will be certain points that cannot be achieved by any
Yeah,
algorithm.
yeah. So we have a lower bound, for example, for that.
Mhm.
We-
And you try to match that.
Yeah, but we have many ways, maybe we cannot match exactly that lower bound. So
What is the question? Yeah. So maybe we cannot match them, and then what?
suppose for each algorithm, the curve is a line, but the slope is different, but there's always something here that we cannot get close to. Okay, So which one of these lines you are gonna choose? We haven't defined the notion which line is better because it is no line is strictly under the other line. For example, another curve would be intersect
Is your
that
question
curve.
something like, if, for example, for one algorithm, my RC curve is like that, for another algorithm, the RC curve is like that, which one should I pick?
Yeah, it is not necessarily exists an algorithm which
And I
minimizes
didn't
for
say,
every
I didn't
point.
say it's an algorithm that minimizes. Did I say that? All I said is that we try to design an algorithm where C lambda and R lambda are as small as possible. And
What does it mean as both of them are as small as possible?
like, well, so I agree with you that in some sense this is not comparable with that one, but then I can say, for example, in this particular lambda, this algorithm is performing better than the other. Like, let's say this point is achieved by algorithm one at point lambda, this point is achieved at lambda prime, then I can say this algorithm is better than the other one. Because
Yeah.
point,
Yeah, so what you're gonna
so
say?
your question is about if I give you two numbers, how do you compare them? Like if I give you pairs of numbers, how would you compare that? It depends on the application. This is what I was trying to say also at the beginning. Like for example, if you have also some side information that your prediction is accurate, then you want to put more weight maybe on C. Like for example, if I tell you that your prediction is very accurate, we design an algorithm where the C one is pretty large versus the other one where the C one is a small, then I prefer the one that has a smaller C1. Let's take it offline, okay? Let me try to show you the application. But bottom line is, you try to have a 2D parametric curve as the frontier of robustness and consistency that is as small as possible. And the small, what does that mean? So in some senses, you can say this algorithm is Pareto dominating the other algorithm, but not all the time. I don't know if anyone has any better answer.
It's like offline.
All right, so a ski rental. Let's revisit that problem and see how we can incorporate ML algorithms into that. I think one thing that I like about a ski rental is, the ML prediction is kind of clear what it should be and how to, in some sense, incorporate that. So what was the ski rental problem for those that are newcomers? Let's say N is the length of the ski season. You're a decision maker. Your goal is to ski throughout the entire ski season. In each day, you have the option of either renting a ski and pay $1 or buying the ski. So you can rent the ski and then you pay $1. Or you can buy the ski and then you have to pay B. And think of P as a number that is way larger than 1. For example, if you know the length of the ski season as a decision maker, here's what you need to do. So if B is smaller than N, that means buying the ski during day 1 and just skiing with that is always better than renting. And if B is larger than N, you want to basically rent the entire time. So the optimal solution always either buys or rents all the time, depending on whether B is smaller than N or B is larger than N. So write it down. B is larger than N, then 5. And if B is greater or equal than N, rent all the time. And then the ski rental problem is difficult because you don't know the length of the ski season and you want to make these rent buy decisions in an online fashion. in some sense, it's a stopping problem, meaning that you're gonna rent, and at some point you decide to buy. And you would like to minimize the cost of renting and buying this case, no matter what n is. So a simple two approximation algorithm for this problem, Varun discussed in the previous class, in last quarter, is the following. I can essentially rent a skis until day B, P minus 1. And then if I get to day B, I'm gonna buy. So the algorithm is you rent for the first P minus 1 days. If the ski season ended, you are happy, you actually got the optimal solution. If the ski season continues, you are gonna buy on day B. And then the point is, there are two cases, whether n is larger than B or n is smaller than B. So if n is larger than B, your cost is going to be 2B minus 1 because you rent for B minus 1 days and then you buy for another day, so it's 2B minus 1. And the cost of the optimum solution is just B because optimum is going to buy at the beginning. So your cost is at most twice the cost of the optimum solution. Right, so deterministic algorithm. Rent for B minus 1 days, buy after. And then the simple theorem. This algorithm is two approximation. It's too competitive, and the proof is, as I mentioned, so if B is smaller than n, then the algorithm is gonna get 2B minus 1, right? Because you definitely rent for B minus 1 days and then you buy on the last day, so that means 2B minus 1. And then if B is greater or equal than, and here opt is gonna be B, because opt knows that it should buy the ski. And if B is strictly greater than n, then you're gonna rent throughout the season, so alg is gonna be equal to n, and opt is also equal to n, so there's really no differences in alg and opt. That means your cost, no matter what n is gonna be at most twice opt. That's a two competitive algorithm. So here's the first question. Suppose we want to undo this problem with a machine learning advice. What do you think is the most natural prediction or advice here? N, right? So and then, so okay, let's do that. So n prediction is going to be what a prediction is telling us about the length of the is estimated length of the ski season. And so this is the advice. So back to your question, Pepper, so why did I leave everything open? This is not an algorithm, right? So this is just like an advice that you get. And then given this advice, what would be the most natural thing to do?
Act it's true.
Right, it's trying to solve the optimal offline, assuming that the prediction is accurate, meaning that if n of prediction is smaller than B, I'm going to rent. If n of prediction is larger than B, I'm going to buy. So this is what I refer to as following that. So if your algorithm trusts the prediction, let's say you're in the domain where lambda is equal to 0. Yes.
Wait, so concretely, is it solving the offline problem optimally using that as if it was true? Is that like how we should think of the definition of C of P I?
You don't need to even restrict your attention because so if your prediction specifies the entire problem instance, then yes.
Okay.
So think of it this way. So the prediction reveals something about the problem instance. Given whatever that is revealed from the prediction, do the best thing you can do. For example, the prediction, assuming the prediction is accurate. This is one way of defining it, right? Assume the information that is given from the prediction is accurate, that will reveal something about the problem instance. Given that, do the best thing. So this is one way of following your advice. But even that is kind of a flexibility. So you can follow your advice in different ways. Yeah, this is one thing that some people don't like about this literature. And at the same time, this is something that some people like about this literature because you can be creative about how you define the prediction, especially when it comes to other problems. For a skill rental kind of, when you think about it, there is really no other alternative. But for example, even for online matching or display ads, you can think of so many different ways of defining a prediction. And once you define the advice, following the advice also can have different meanings. Here again, it's kind of like unique. Okay. All right, so if my lambda is equal to 0, that means I trust the predictor 100%. Then given access to this number, my algorithm, the most natural thing to do is basically follow the prediction. But then this might be bad because maybe your prediction is very off. And therefore you won't be able to competitive against any problem instance. So what would be a natural way to use the prediction at the same time you guarantee that you are competitive against any problem instance? And as a hint, in order to be too competitive, all you needed to do was waiting a little bit up to time p-1, and then doing the buy decision. Now, suppose you have the prediction, you don't want to immediately follow the prediction because this is equivalent to not hedging against the situation where the prediction is inaccurate. If you want to hedge against that, what should you do? Yes.
Weighted average.
Weighted average, meaning that you look at the average of the
B and prediction.
Okay. How do you want to incorporate parameter lambda?
So the weight is lambda. So it will be lambda times B plus 1 minus lambda times N of prediction. Or the other way.
This is interesting. So I guess another way of what you're saying is that with probability lambda, I do the deterministic algorithm. With probability 1 minus lambda, I'm going to follow the advice. This is always one way of getting a robust and consistent algorithm, right? So you flip a coin at the beginning. With probability lambda, you do the deterministic algorithm. With probability 1 minus lambda, you do the following the prediction.
I might be wrong, but I think you meant like setting the threshold to be a complex combination of N that this guy predicts,
right,
or of the two thresholds, the threshold given to you by like following it completely and the offline.
It's different from the algorithm I have. So you're saying that, so you wait for N prediction times 1 minus lambda plus lambda times B.
Minus 1.
Minus 1. Yeah. I think it's a good choice. I can't disprove to you off the top of my head that it's going to be better than a simpler suggestion I have. But let's think about that also. Is it? It's aligned with the one the simpler one that they have in mind. So the simpler one is just waiting for lambda. So let's say, this is the first ML algorithm that we designed.
Waiting for lambda B.
Lambda B. Yes.
Means you discarded the end prediction.
Oh, so I'm waiting for lambda B times, and then after I follow the prediction. I don't need to buy after. So if the predictor says don't buy, then I'm not going to buy. But if the predictor says buy, then I'm going to buy. So let's do that. So my algorithm is wait for lambda B rounds, then follow the prediction. And if the prediction, for example, says that hey, you should not buy, but then the ski season doesn't end, then you're forced to rent, and you're going to rent for it.
So when you say follow the prediction,
Basically, if the prediction says buy, just buy.
so yeah, but the prediction at time 0, not prediction at time lambda b. The prediction at time lambda b could be different. Like, so the prediction is only giving you n pred. And the optimal
prediction,
thing.
you just talk to prediction once. So you talk to your predictor once.
Okay.
You tell the predictor, should I buy or not? And the predictor says that, hey, this is my number. It is greater than buy, so you should never, it is greater than B, so you should never buy. Or it says it is smaller than B.
But I'm thinking of a simple algorithm which seems better than this. Maybe you have a counterexample. So
No, this is not the optimal algorithm. It's just like one algorithm to give you an idea why you can do better than flipping a coin because lambda going with deterministic.
okay, I was thinking wait for lambda b rounds as you did, and then at lambda b plus 1, you basically look at n pred. And then you look at,
But the emperor doesn't change.
yeah, it doesn't change. You just like reevaluate your life, like, I guess. And then you look at 1 minus lambda. I mean, I'm just saying you look at the number of remaining days before which you would have bought had you believed n pred. And if this is smaller than b, then you don't.
I guess what you're gonna say is that
Buy.
if already lambda b
Yeah,
have
exactly.
passed,
It
then
doesn't make sense to think about it anymore. Like if n pred, yeah, exactly. So if n pred minus lambda b is greater than, smaller than b, then just keep
Sure.
renting.
But in the worst case, it's gonna. I mean, you can't analyze that algorithm and get any better bound. It's gonna give you the same.
Okay.
But I agree with you that that is a better algorithm. But the one I'm saying is even simpler. It's just like wait for lambda b rounds, then follow the prediction if it says buy, otherwise don't buy. And as I said, if for example the prediction says that hey, you should not buy, and then you basically rent for lambda b rounds, then you rent after that as well. And yeah, and if it says buy, you rent for lambda b rounds, and then you just buy right after. So we want to show that this algorithm has deterministic lambda. So we show that the deterministic lambda is something like C lambda, R lambda, consistent robust, where R of lambda is 1 plus lambda, and C lambda is ordered 1 over lambda. And let's try to show this. Before going further, so one thing that I wanted to tell you is that if lambda is equal to 1, which is the case that you don't trust the predictor at all, the competitive ratio you get is 2, which is what this deterministic algorithm can get. And actually, this deterministic algorithm is the best deterministic algorithm for this problem in terms of competitive ratio. So in lambda equal to 1, you get the optimal competitive ratio. You are as good as the one that ignores the prediction. And then for any lambda between 0 and 1, you have.
If lambda is between half and 1, you are still happy because the C lambda bound would.
Right.
So actually, algorithm clarification. So you're saying if the algorithm just predictions are predict, you says rent, you keep renting, but that could be infinite, right? Would you still want to buy at day B or not? Even in that case, otherwise I don't know how you even get R.
I mean, If the ski season ends, then you're not gonna continue rent.
No, but you would have bought, right? Like if the ski season was very long, it keeps say renting, then the cost could be very high if you follow prediction.
Yeah,
So you should still
n could
buy.
be infinite. So n could be infinite and n rate could be something finite. I think there are multiple scenarios where like you should just ignore it. For instance, when lambda b is bigger than n rate, or when n pred has already passed. Yeah, in that case, n pred would already have passed, and there's no
This is
point.
the reason that you get order bound over lambda here. So basically, if I have 100% trust in the prediction, and the length of the ski season is infinite, then I'm not gonna actually.
But even half, let's say, right? So that algorithm says wait for b over 2, and then both of these are constants. But I'm just wondering how you're going to get a constant, because if it just says keep renting, you'll keep renting, but and your cost is infinite. Whereas R lambda says I should have a bounded cost, some constant times p. So I should still buy eventually.
No. R lambda times the cost of the pi thing, right? Which is also infinity.
So, but I get min of R lambda opt and the splits. So I should not get more than 4 opt, 4p or something. So I should still buy eventually, right?
You should buy eventually. You mean after P rounds, you should buy?
I think.
I mean, that's always a better algorithm.
So the algorithm I mentioned would probably have these properties, because follow the prediction until it makes sense. Like you would not follow the prediction if n pred is smaller than lambda b. That's not rational.
But then you're just doing the same as thing because they keep renting, right? So that then you do the right. N pred is lambda b less than lambda.
So if n pred is less than lambda b,
Then you're doing opt.
yeah, and then you just buy at that point, right? I mean, then you'd not listen to the prediction at least, is what I'm saying. If the prediction would have
Only when pred is bigger than b, you buy at lambda. Otherwise, you just keep renting. Oh, I see. No, I see. What happened?
So if you rent for lambda b rounds, then after that, if the n pred is larger than b, you are gonna, if n pred is smaller than b, you're gonna keep renting.
But now once
To end.
you know n pred is wrong, you'll still not buy. You'll still keep renting even beyond n pred days of snowing.
yeah, which would have that example which you mentioned, right?
But then the cost could be infinite. So I'm not really sure if. So
I think we need to define what follow the prediction means here.
Yeah, something doesn't work here, right?
Maybe we should write the proof and then
The proof I have in my head actually breaks too. When you look at the case when n is much larger than n pred. Okay, so I'm gonna give you the correct version after the lecture. So, all right, to be fixed. That's fast because I want to actually build on top of that. Now, I can reveal to you what the other algorithm is, but let me then try. Yeah, okay. I have to send you guys a notes how to get a deterministic algorithm that is robust and consistent. This one is not. So let me continue by switching to something that I want to tell you after that, and then this one is less intuitive, but at least it is correct. So the idea is the following: for the SQ rental problem, there is a primal-dual algorithm that we saw in the previous class. Let me remind you what that algorithm was. So the idea is looking at the fractional version of the SQ rental. So at each time I, the algorithm decides on fi, which is the fraction corresponding to rental, and also decides on x, which is how much the algorithm should buy. Just recalling the previous class. And then you can basically write on a linear program for the optimal offline problem. So you try to minimize x times b plus summation I from 1 to n f of I, such that for every day in the ski season, some I from 1 to n, for every day in the ski season, fi plus x is at least 1. And then x and fi's are all greater than. So this is the LP for the optimal offline problem for the ski rental. So this contract essentially means that for every day, either you have bought the ski at the beginning of the season or you rent. So for every day, sum of x plus fi should be greater than 1. Okay, that was the LP that we saw. Yes.
May I say something about that?
Yes.
Can we adjust it to buy at maximum of lambda b plus maximum lambda b and n break plus 1?
I think that might work actually. Yeah. I think that's
Because first purpose, what if lambda is 0, for example, we wanna trust completely our prediction. We say if we pass n prediction, our prediction is wrong, so we're gonna buy. And but we are now adding some lambda b threshold to just wait at least at lambda b and then do the same thing. If now you have passed n prediction, just buy. If not, do the same thing. Wait until n prediction plus 1 and then
Prediction. So basically you're saying I'm gonna rent for lambda b days, then if the prediction says buy, I'm gonna buy. If it says rent, I'm gonna rent.
it's different.
yeah, do what prediction is saying, but until time and prediction comes. After that, I'm gonna buy. If n is greater than n prediction plus 1, I'm gonna buy at that.
Actually, it should be min of lambda b and prediction.
So let's keep that off. There is a fix for that, but I need to think about it. It's more or less something like that. All right, back to the LP. So this is the LP for a ski rental problem. And then we had this dual, which is a maximization problem. So you're trying to maximize, let's say, summation by I from 1 to n, such that first of all, yi is between 0 and 1. And what else? So we want to say the summation by I from 1 to b, I from 1 to n to be at all. And by I is great, and is between 0. So it's a primal problem. This is the dual problem. And the Primal-dual algorithm for a ski rental is working in the following way. Let me remind you what the algorithm was for the fractional version. The Primal-dual algorithm. At each time, so it keeps track of basically just one number, which is the primal variable x, and based on that, decides on what fi should be, how to update x, and how to set yi at that time. So at each time, so at the beginning, x is equal to 0, and all the fi's are essentially equal to 0. At each time I, if it happens, meaning that n was greater or equal than I, you first start by setting fi to be equal to the current 1 minus x. All right. And then it updates x by the following rule. So x is going to be the previous x multiplied by 1 plus 1 over b plus 1 over e minus 1 times e. Let me call this a c because it is kind of important in the way I'm going to modify the algorithm. So this is the primal update. On the dual side, what it does is just increases the dual by 1. So yi is going to be equal to yi plus, let me call this one c prime. It's the dual update. And we know in the vanilla version, when there is no ML advice, C is actually equal to E, and C prime is equal to 1. I'm not going to show you where these numbers are coming from in the interest of time, but I trust that you remember from the previous course. And then we can show this algorithm is 1 minus 1 over complexity, which is the optimal complete algorithm for this one. Now, the question is, okay, so I have this machine learning advice and prediction, and somehow I want to include that in this algorithm structure. How can I use the machine learning advice in order to change my primal update and maybe the dual update? So if you remember the way that we analyze this algorithm, so we are saying, well, so x starts from some initial value, and then you multiply that by 1 plus 1 over p at each time. So in some sense, you become more and more aggressive in buying as this number becomes larger and larger. And you become more and more aggressive in renting as this number becomes smaller and smaller. And now if you want to incorporate the predictions, somehow you want to say, well, so if the prediction is saying buy, if I trust the prediction, I should increase this number so that I become more aggressive in buying. And if the prediction is saying that, hey, the number of predicted days is smaller than B, so you're better off renting. Again, if I trust the prediction, I want to make this number smaller so that I rent more, or I rent more aggressively. And now the question is, how would we do that? I'm not sure if there is a systematic way of finding the right trade-off between R lambda and C lambda by just like looking at this algorithm. But here is a theorem. Consider the following version of experimental Primal-dual algorithm. Let me call this Primal-dual with two parameters, C and C prime. So really C is the one that gives you the final solution because primal only matters. C prime is only for the sake of analysis later. So what is my version? So you look at your prediction. So if the N prediction is smaller than B, or less than or equal than B, which means that you're better off renting, then run the Primal-dual with the following choice of values. So I set C to be e to the power 1 over lambda, and C prime to be lambda. Otherwise, run the Primal-dual algorithm when C is equal to e to the power lambda and C prime is just 1. Then this algorithm is R lambda, C lambda, robust, consistent, where C lambda is equal to lambda divided by 1 minus lambda, and this is actually notation, but kind of funny. So it's lambda over 1 minus, let's say e to the power minus lambda for now. And R lambda is equal to 1 over 1 minus e to the power minus. So if you sanity check, so if lambda is equal to 1, then the two numbers are equal to each other, are equal to 1 over 1 minus 1 over e. It's a cost minimization problem, so it's a 1 minus 1 over e competitive algorithm. And then, as you see, if lambda becomes small, like lambda becomes, let's say lambda converges to 0, this converges to 1 in the limit. And at the same time, if lambda is equal to, let's say 0, this is pretty bad, but then you're actually trusting your predictions. So it doesn't matter that you're not very much competitive. So this is essentially what you get from this out. And then for any lambda between 0 and 1, both of them are kind of constant. All right, so let's try to prove this theorem. It's not actually that difficult in the remaining time that we have. Whiteboard. The proof. So the proof is essentially a modified version of the Primal-dual analysis of experimental that we saw in the previous course. How to do that? So we are gonna first show with these choices are constructed dual. No matter whether you're in this board or in the other board, is gonna be feasible. And then we are going to look at the change in the primal objective versus the change in the dual objective, and we try to bound the ratio. I don't know why did I erase the LPs. Because of that call. Here, so minimize b times x plus summation I from 1 to n fi. Primal, and then the dual is your maximizing summation by I. So let's look at two cases. Case one. Suppose the prediction says that, hey, the number of days in the species is actually larger than.
Is that rule correct? I mean, you wrote the same thing before as well, but I'm just asking if it's correct. Because this is just
Summation
B.
y I should be.
Oh, sorry, I mean, this thing, the max thing is B. The max is just B. I equals to 1, 2, and y less than equals to B. And that's the objective as well.
Sorry, what's the question? So
The objective and the constraint look the same,
Yes,
and it's a maximization problem.
yes. But y I should be between 0 and 1. And we don't know whether n is larger than b or not. It's kind of a weird law, but I agree. I'm praised for it. So let me do it also in a different. So this is a proof, let's say for robustness, which is a little bit easier. So the robustness proof. I want to show that no matter what problem instance I have, my algorithm is going to be 1 over 1 minus e to the power minus lambda complex. So we look at the first case. So when number of prediction is greater than b, the number predicted is greater than b. So in that case, we are going to update in the following way. So c is going to be equal to e to the power lambda, c prime is going to be equal to 1. So here's a simple question I have. How many times am I going to update x before it hits 1? Yes.
Robustness is compared to optimum online or optimum offline.
What does optimum online here mean?
That this one, the lower algorithm.
Oh, you mean the
Like
deterministic algorithm?
Yeah.
No, I mean I'm comparing with the optimum offline. The actual optimum for the problem is. So basically robustness is just like the previous thing that we have always been doing. So you wanna show the algorithm is 1 over 1 minus e to the power minus lambda complex no matter what.
So you mean if lambda is 0, in that case R0 is 1?
If lambda is 0, R0 becomes very
Not in that case. Here.
Which case? Here?
Yeah. If lambda is 0, then R0.
Maybe a flip.
Yeah.
Oh, I see. Maybe that was the issue.
I think RNC may be flipped.
Right. Yeah, forget about these parts of the price. Don't look at this part. There's something conservative around here that I don't know how to fix it now. All right, back to the analysis. So we were saying is the following. So we keep increasing the primal as days move forward. And now I'm looking at the following. So every time that you update the primal, so what I'm trying to say is that
When the switch is 1.
yeah, so I need to again consider two cases, right? So now when you're in this board, suppose n is smaller than b or n is larger than b. You have to consider both. Right. So if n is smaller than b, then I'm going to start with the initial value for x, which is 1 over c minus 1 times b. And then every time that the primal is updated, it's going to be multiplied by 1 minus 1 over b, right? So that means this term multiplied by 1 plus 1 over b plus 1 plus 1 over b to the power n is going to be so this is going to be how much x increases throughout the process. Right? And so this is going to be basically how much x you get. What I'm gonna do? Oh, and we know. Oh, so here's the point. So you know when x becomes 1, this is the moment that you stop renting. Therefore, you're gonna increase this n until this point. So in fact, I didn't even need to consider 2 cases. What am I trying to say is that every time that you increase this x, y is going to increase by c prime. That means if you start from 1 over c minus 1 times b, and then you have this as the first day, 1 plus 1 over b as the multiplier of the second day, so on and so forth. If you look at the last one, this is going to be 1 plus 1 over b to the power of summation yi's. And you know this process has continued until the point that x hits 1. So the moment that x hits 1, then you're going to stop. That means this is going to be at most 1.
Why is summation of y?
C prime is 1.
C prime is 1. So in each iteration, you increase C prime by 1, and C is equal to e to the power lambda. I think this is fine.
What?
I just want to show that the dual is
Why summation? It shouldn't be the last y? C prime is
Oh,
1.
yeah, it should be maybe max.
Question 1 is how many rounds you have right now. It's a geometric sum of x. Wait, x is geometric sum.
You increase it as many times as the final y.
Summation by x.
No, final y.
There's a different by.
All are
There's a
different.
different dual variable for each layer.
yeah. So it's not the same I, right? So this is time I. In each time you just add the dual of that. You add 1 to the dual of that round. And what I'm trying to say is that at the end of the day, the summation of yi in this process is going to be at most b. And the reason for that is because
Because of. So you want to prove dual is feasible, right?
right.
We can, I think we can get it from the.
So my understanding from this is that at the end you can say you will have at most lambda times b of x.
think it might work out. The number of updates is summation yi, right? So if you just upper bound it and take the logarithm and everything, you get number of updates upper bounded by lambda over log 1 plus 1 over b.
Yeah, so from this, you can imply that the number of updates is at most lambda times b. But is that, oh, that's enough because, yeah, okay. I don't know why I'm confused. Because lambda is at most, okay, so this is actually helping with the feasibility. This is why I was confused. So thinking about this process, that you're increasing x in this way and increasing y in this way. That means at the end of the process, definitely this total should be at most 1. But when x reaches 1, then you should stop. And then what is this left-hand side? So this is equal to 1 over c minus 1 times b times 1 plus 1 over b. And there's, I should subtract 1 from the end because the first one is here. This 1 plus 1 over b to the power summation by I minus 1 divided by 1 over b. This cancels this one. And we know this is at most 1. Now, if the c is set to be some number which is equal to e to the power lambda, then I can say, well, if I divide this by lambda, multiply by lambda,
But summation of y is number of updates. So you just send it to the other side and take a log.
right. So if summation of yi's, I will claim that from this you can conclude that summation of yi is actually at most lambda times b. Let's see why is the case. Because if summation of yi is at most lambda times b, then this term 1 plus 1 over b to the power lambda b divided by lambda times lambda will be upper bounded by e to the power lambda. So this term is going to be upper bounded by e minus 1, e to the power lambda minus 1. C is e to the power lambda minus 1. So therefore you get what you want.
I think you can just multiply both sides by c minus 1 and you get what you want.
Sure. So what I'm trying to say is that when this condition holds, it is equivalent to summation of yi is at most lambda b. So at termination, this should hold, and lambda is a number between 0 and 1, so therefore the dual is going to be fixed. Okay. This is essentially the previous proof for the SQ rental, but doing it with the new modified C parameter. And then when you compare the change in the primal with the change in the dual, so let's look at that part. So the delta primal in each step of the algorithm is equal to what? So it's going to be equal to V times how much x increases x divided by b plus this term. So it's going to be b times the x at that time divided by b plus b times 1 over e to the power lambda minus 1. This is from the x side. And then you have to look at fi. Fi increases from 0 to 1 minus x. And that is going to be a 1 minus x here. And there was a b here, right? Because that's 1 over c minus 1 times b. So this cancels this cancels this. So you're going to end up with something like 1 plus 1 over e to the power lambda minus 1, which is e to the power lambda divided by e to the power lambda minus 1, which is 1 over 1 minus e to the power minus lambda. That's the change in the primal. And then the change in the dual initial step is just equal to 1. And that's how we can show the robustness. But you don't need to consider the prediction when you think about robustness, but there was no need for a case analysis. This was the feasibility proof. Sorry, it was a little bit messy.
Why was there no need for the case? Because if there weren't any case, I couldn't have set c equals to e to the power lambda.
What was the question?
So in the algorithm, you can set c to e to the power lambda and c prime to 1 only when n pred is greater than b. So I think,
N prime is greater than B.
so I think the case was correct. You have to have a case.
I mean, it really doesn't depend. Right. Because you do the big octave when n pred is greater than B. So we need to actually look at the other case for robustness here. So the other case for robustness, let's do it on this whiteboard. It's just repeating the same thing over and over again. But you get the idea. So case 2, when n pred is smaller than B, so we do the small update, meaning that we go with c equal to e to the power lambda and c e to the power 1 over lambda and c prime equals to lambda. Then when you think about the dual feasibility, you increase x again until the point that it hits 1, and then after that we'll stop renting. The condition is exactly the same for termination, meaning that as long as 1 over c minus 1 times b times 1 plus 1 over b all the way to 1 plus 1 over b to the power summation by I minus 1 is smaller than 1, you keep adding the duals each time by c prime, and after that you terminate. Now, with the new c, what this condition would be, so this is going to imply that I claim the summation of yi from 1 to summation yi from 1 to whatever. It can be the number of days, or it might be when you terminate. Again, it's going to be at most b, and the reason is the following. So, this is not summation. It should be summation of yi divided by lambda, right? Because the number of times that you increase each time you increase yi by lambda, so the number of days will be summation of yi divided by lambda. And why it is the case? Now c is equal to e to the power 1 over lambda. Again, do the following. So I'm dividing by b, multiplying by b. Do you see that, or do you proof? So basically what I'm saying is if summation by is at most b, then this term is going to be equal to 1 plus 1 over b to the power summation by I over lambda minus 1 divided by 1 over b, and then you get a 1 over c minus 1b from this side. So if summation by is at most b, then this thing is going to be at most 1 plus 1 over b to the power b over lambda minus 1. And this is at most e to the power 1 over lambda minus 1. This is again at most e to the power 1 over lambda minus 1. And c is e to the power 1 over lambda. And again, this is going to be at most 1 because of that. The person who is describing, I think you need to write down this algebra correctly. But the essence is basically looking at this summation, saying that, hey, if this is true, that implies that summation by is at most b, simply because, the moment that summation by I becomes b, this left-hand side will be strictly larger than 1 by following the rest of the calculation.